Engineering properties of rocks. Intact rock and rock mass. Intact rock, rock material. Rock containing no discontinuities, rock mass. Mass of rocks interrupted by discontinuities. An intact specimen may be considered isotropic, but lateral and particle variation in properties makes a rock mass anisotropic and heterogeneous than intact rocks. An intact specimen may be described by standard geological terms such as rock name, mineralogy, texture, degree and kind of cementation and weathering. Rock mass may be described by combining both intact rock properties and discontinuity properties. Intact rock mass properties are intact rock strength, discontinuities in rock mass, condition of discontinuities, weathering of rock mass. Intact rock strength. It is the amount of stress applied at rock failure or rupture. The applied stress may be compressive, shear and tensile in application, giving rise to compressive, shear and tensile strengths. Influencing factors: composition, texture, grain size, kind and amount of cementing material and moisture content. Index tests are the variety of field and laboratory tests that provide estimates of various engineering properties of intact rocks. Of the index tests available for predicting uniaxial compressive strength and modulus of elasticity, the point load strength and Schmidt rebound hammer tests are most commonly used. Discontinuities in rock mass. Rock masses are heterogeneous and anisotropic because of differing rock types, presence of discontinuities and varying degrees of weathering. Statistically homogeneous region is identified first. Such region includes a portion of a rock mass which contains same rock type having similar weathering condition and same number of joint sets and their similar orientation distributions. Characteristics of discontinuities. For each statistically homogeneous region, joint properties are measured that includes orientation, spacing, persistence, surface characteristics, aperture, opening, infill material if present. Shear strength of discontinuities surface are dependent on one or more of these factors. Orientation. It refers to deep amount and deep direction of a discontinuity. It controls mode of failure, daylight situation and mechanical anisotropy. Spacing. It refers to the perpendicular distance between two adjacent discontinuities. It affects overall rock mass strength, excavation method, and support system. Spacing increases with depth, except in faulting regions. Continuity, persistence. It refers to the continuity or areal extent of discontinuity and is particularly important because it defines the potential volume of the failure masses. Failure mass. Intact rocks or rock bridges may interrupt persistence. Surface characteristics. Waviness or undulation of the surface, smaller scale roughness of the surface, physical properties of any infill materials are important. Aperture is important for fluid flow and shear strength along the joint. Weathering of rock mass. Physical weathering results in changes in size and number of discontinuities present in rock mass. Chemical weathering is enhanced by movement of groundwater through the networks of discontinuities. The negative influence of physical and chemical weathering on rock mass strength or quality is apparent as it weakens the whole rock mass. Rock quality designation RQD. The RQD value is the percentage obtained by dividing the sum length of all core pieces equal to or greater than 10 cm long by the core interval length. Smaller pieces and or core loss are assumed to result from closely spaced discontinuities, shearing, faulting or weathering, all of which decrease rock mass quality. An RQD of 100% indicates 100% core recovery with all pieces equal to or greater than 10 cm in length. Thus, it doesn't imply any unjointed rock mass. Another empirical method of estimating RQD value employs the number of discontinuities per unit volume. Total number of discontinuities JB in a cubic meter of rock mass is counted and is used in the following equation. RQD equal to 115 minus 3.3 JB, where JB is equal to sum of the number of joint per unit volume of rock mass, volumetric joint count. Rock mass classification system. The strength of an intact rock sample and that of a rock mass of the same rock type differs greatly. The intersecting joints reduces the strength of the rock mass. So there is a need to have a acceptable universal classification or rock for geotechnical purposes. The more universal the intended use of the classification, the greater the number of intact rock and rock mass properties that must be measured for the classification. No single parameter or index is present that can fully and quantitatively describe a jointed rock mass for engineering purposes. Various parameters have different significance, and only if taken together can they describe a rock mass satisfactorily. There are but various rock mass classification systems developed by many investigators, and couple of them are most widely used. Rock mass classification. Terzaghi's descriptive rock mass classification for estimating tonal support requirements was developed in 1946. Presence, number, and character of discontinuities and degree of chemical weathering were the basic parameters. Rock mass strength classification of zone, 1962. It quantified zone spacing and degree of weathering and added the intact UCS of the rock. Rock structure rating, RSR classification of Wickham et al. 1971 was designed for tonal support application. It combines the effect of rock types and structure, joint spacing and orientation, and joint condition and anticipated water inflow for use in designing tonal support system. By Nowak's Geomechanics Classification 1974 RMR uses RQD, UCS, and spacing, separation, continuity, and orientation of joint and groundwater flow. Q system classification of Barton et al. 1974 of Norwegian Geotechnical Institute NGI requires RQD, number of joint sets JN, joint roughness JR, joint alteration JA, water flow in joints JW, and rock stress reduction factors SRF. Rock mass quality Q is equal to RQD by JN into JR by JA into JW by SRF. Geological Strength Index GSI of Hoek, Hoek 1994 and Hoek, Kaiser and Bowden 1995 depends on properties of intact rock pieces and also upon the freedom of these pieces to slide and rotate under different stress conditions. By Nowak's Geomechanics Classification or Rock Mass Rating RMR. In this classification method, the various parameters are rated and then summed to give the rating of the rock mass, with higher rating indicating rock mass of strong quality. The following 6 parameters are used to classify rock mass using this method: uniaxial compressive strength of rock material, rock quality designation, spacing of discontinuities, condition of discontinuities, groundwater condition, and orientation of discontinuities. This classification system is applicable and adaptable to many different situations, including coal mining, hard rock mining, slope stability, foundation stability, and tunneling. The output from the RMR classification method tends to be rather conservative, which can lead to over-design of support system. Q system of rock mass classification. This system of rock mass classification was developed in Norway by Barton et al. 1974 of Norwegian Geotechnical Institute (NGI). This system was proposed on the basis of an analysis of 212 tunnel case histories from Scandinavia. It is a quantitative classification system and facilitates the design of tunnel supports. The main difference between RMR and Q is the fact that RMR system takes into account the condition of all discontinuities, whereas the Q system considers the unfavorable discontinuity set only. This system is based on numerical assessment of the rock mass quality using 6 different parameters: RQD, number of joint sets, roughness of the most unfavorable discontinuity, degree of alternation or filling along the weakest joint, water inflow and stress condition, stress reduction factor. Q is equal to RQD by Jn into Jr by Ja into Jw by Srf. The first question is the crude measure of the block size. The second question represents the roughness and frictional characteristics of a joint walls or filling materials. The third question consists of stress parameters. Excavation support ratio (ESR) is related to the use for which the excavation is indented and the extent to which some degree of instability is acceptable.